All right, guys, this is lecture 29. I am lecturing from home today because my family is sick, and because of that, I've changed my background here to space. Very exciting. I know a lot of you are confused and concerned about how canceling the final will affect your grades. We are working through that, the faculty teaching Chem 105. We're all working through that together at this time, so we should have some more information for you shortly. Okay, so in the meantime, you're just going to have to wait and be patient with us while we work through all this crazy stuff. Hopefully, none of my kids will interrupt, but I imagine if I do enough of these from home, we will get some interesting things happening. Okay, now you'll remember a couple weeks ago in class, or a couple days ago, somebody asked how Sarah Palin relates to chemistry. Of course, the answer is she doesn't. But as soon as I went to my office that day, I sat down and in my news feed saw that Sarah Palin was unmasked as the bear in The Masked Singer. I said she had been yelling at a bear, but apparently she was just pretending to be a bear. All right. Now, what we're going to talk about today is stoichiometry. So stoichiometry has to do with chemical reactions, which is likely what you thought we'd be talking about most in this course. But again, a chemical reaction, in case you've forgotten, since we've just been talking about orbitals and quantum numbers and other fun, crazy things, chemical reaction is a process that changes the composition of your structure. So it changes your identity here, right? So a good example of this is putting sodium metal in water. Some of you might remember this is the reaction I tried to get to work early in the year. You use too small of a piece of sodium. So I have a video of somebody doing it a little better with a slightly bigger piece of sodium here. So we got it to that spinning ball part at the beginning. We didn't quite get to the flame. Next time I do this, I'm going to have to use a much bigger piece of sodium. Right? So but that's what happens when you throw sodium metal into water. And so the products of that are sodium hydroxide and hydrogen gas. Another great chemical reaction is what we call elephant toothpaste. And this is when you take hydrogen peroxide, which is H2O2, not H2O. If you throw another O in there, it becomes reactive. And if you react that with I-, usually found in potassium iodide, you get a really fun reaction. I have another video for that.
The main ingredient for elephant's toothpaste is hydrogen peroxide. It's the same stuff you pour on a scrape to disinfect it. The thing is, the bonds that hold the hydrogen and oxygen together are pretty weak. So if we poured some of this in here and just left it for a while, it would keep releasing oxygen and eventually you'd be left with just water. However, if you add a catalyst like potassium iodide, you can make that slow process happen almost instantly. So that's cool, but we can make it way more impressive if we add one key ingredient, soap. So if we pour this in and then do everything else the same, now when the oxygen is released, the soap captures it, creating bubbles and foam. And then finally, if you do all that again, only now you add food coloring and use a flask that tapers like this, you can focus the expansion of foam so it looks maximum awesome.
All right, so in that reaction, the food coloring and the soap weren't actually part of the reaction. They were just fun little extras to make it look cooler. But what we're talking about here, or what I've been showing you, is chemical reactions in the form of equations. So we've seen a few of these before. And in chemical equations, we start with our reactants over here on our left, and we have our products over here on the right. So in a chemical reaction, the reactant is the species that gets consumed or used up, and the product is the thing that gets produced. So when we write these, by convention, we write our reactants on the left, and we write our products on the right. So this is the same way as you read in English, right? You start on the left and go to right, and that's exactly why we have the reactants on the left and the products on the right. Additionally, in a chemical equation like this, it's usually good form to show what state of matter these guys are in. So here we have aluminum as a solid, oxygen gas, and Al2O3 as a solid. Now, sometimes you'll see equations where it doesn't have the physical states, so they're not always requisite, but it's generally considered good form to include those. And then we also have these numbers in front of the different chemicals. These are called stoichiometric coefficients. So these are the ratios of the different species that you need for this reaction to happen, or in the case of the products, this is the number of moles of products you get given the specific number of reactants. Right? Now, specifically, why do we need coefficients? So coefficients are really what we're going to be talking about a lot today. So the reason we need these is because of the conservation of mass. If you remember Antoine Lavoisier, the French guy that got beheaded, so he did all of his reactions in closed vessels and did a really good job of weighing his products and reactants, and found that nothing's created or destroyed in any of these. So you have the same amount of mass in the beginning and the end, right? And so we get this whole law of conservation of mass. Now, how that looks in a specific chemical reaction is more in the terms of a conservation of atoms. So when you undergo a chemical reaction, you have the same number of atoms as you started with, and you actually have the same types of atoms. So for example, in this reaction right here, where we have aluminum reacting with oxygen, we then have aluminum and oxygen atoms in the products. So the number of atoms of aluminum we start with is 4 aluminum atoms, and we end up with 2 times 2, or 4 aluminum atoms. We start here with 3 times 2, or 6 oxygen atoms, and we end up with 2 times 3, or 6 oxygen atoms. So the atoms you start with are the atoms you end with. You're not changing atoms at all. If the atom changes, that's what we call a nuclear reaction, and we're not dealing with that. That's a physics problem. Okay? We might deal with that a small amount later, but really that's a physics problem, and we're chemists, and we don't care about that, right? So in a reaction, the elements that you start with are the elements you end with. Really, you're just changing their arrangement and the way they're bonded to one another, right? And so we need our coefficients here, like our 4 in front of aluminum, to make sure that we have the same number of atoms on each side of our equation, right? Now, I've been talking about these in terms of atoms. So we're starting with 4 aluminum atoms, 3 O2 molecules, and we'd call this guy on the left 2 formula units of aluminum 2O3, and that's because this is a lattice structure that forms a 3-dimensional crystal, right? But we can also refer to these as moles, saying we start with 4 moles of aluminum plus 3 moles of O2. We're going to 2 moles of Al2O3, okay? So when you look at these equations, a lot of students will ask, should I think of this in terms of atoms or in terms of moles? And the answer is you can think of it both ways and it'll work out. You're often going to need to think of it in both ways. And the way you think about it is going to depend on the context of the question or problem you're dealing with. Right? Now, a big part of this, of dealing with equations in stoichiometry, is balancing our equations. So a lot of times we will give you a lot of questions that look fairly similar to this, where we just have a reaction written out with no coefficients, and you're going to have to figure out the coefficients. And so when you're balancing equations, you're going to follow 3 basic steps. And this looks simple, but it gets really complicated the more complicated your reaction becomes. So the first step, which is fairly simple, is write the correct formula for reactants and products, including their physical states. So this is important because if you write this formula wrong, you're never going to balance it correctly. And you're just not going to be talking about the right reaction. Then what you're going to want to do is balance one element that appears in only one reactant and product first. Now this isn't always possible, but for example here we have carbon showing up in CH4 on this side. It's not showing up in any other reactants. And we have carbon showing up in HCN on this side and not in any other products. So we can start by balancing this guy. We're going to say there's one here, one here. We can do the same thing with this nitrogen in NH3. There's one nitrogen on the left, and we can count one nitrogen over here on the right. And that just leaves all of our hydrogens here, which we'll need to balance out. Okay, so if we count this guy, the first thing you want to do is just check, is your reaction balanced already? So if we look at this reaction, we're starting with one carbon on the left on our reactant side. We're ending with one on our product side on the right. The same is true for our nitrogen. We're starting with one on the left. We end with one on the right. Now let's look at our hydrogens. We have 4 hydrogens in CH4. And we have 3 in NH3. So we're starting with 7 hydrogens on our left. And on the right, we have 1 hydrogen in HCN and 2 in H2. So we actually only have 3 hydrogens on the right. Now that is a problem. We need to have the same number on the left and on the right. Now in this one specifically, we're fortunate in that hydrogen gas is all by itself, or sorry, the element hydrogen is all by itself in the form of H2 gas. And so we can actually just give this guy a coefficient to balance out this equation. So what that's going to look like is like this. If we instead say there are 3 moles of hydrogen gas being formed instead of 1, now we have 1 plus 3 times 2, which would be 6 hydrogens. So 6 plus 1 hydrogen would give us a total of 7 hydrogens on the right. We started with 7 on the left. Now we have the same number of carbons on the left and the right, same number of nitrogens on the left and the right, same number of hydrogens on the left and the right. And so this is a balanced equation. Really wish you could ask me questions right now. All right, but let's give this a little practice with these 3 reactions. We're going to go through them just stepwise and figure out how to do this. This first reaction, we have solid iron reacting with oxygen gas, and that's going to give us rust. So rust's formula is iron 2O3. And we need to balance this guy out. So usually I will just start from left to right. I will start with our first element. So here we have iron. We have 1 atom of iron on the left, and we have 2 atoms of iron on the right. Now in this case, I might be tempted to write a 2 here and say there's 2 copies of iron on the left, but I also know that, notice there's this oxygen in here. We have O2 and O3. That's going to be the more complicated one to balance. So let's actually balance that one first, and then it will be real easy to balance the iron. You'll see why here in a second. All right, so we're starting with 2 atoms of oxygen on the left, and we have 3 atoms of oxygen on the right. So the easiest way to balance those out is to find the least common multiple of those 2 numbers, the least common multiple of 2 and 3. The easiest way to do that is to multiply 2 and 3 together. That gives us 6. So we're going to want 6 atoms of oxygen on the left, 6 on the right. So if we're starting with 2 atoms of oxygen right here, how do we turn that into a 6? We're going to multiply it by 3. So now we have 3 times 2 atoms of oxygen. That is 6. Over here, we're starting with 3 atoms of oxygen. How do we turn 3 into 6? We're going to multiply it by 2. All right. Now, originally, I said maybe we should write a 2 in front of this iron, but now we see that on the right, we have 2 times 2, or 4 atoms of iron on the right. So over here on the left, we're actually going to need 4 atoms of iron. Now, when you do these problems, you want to go through and double check that everything is right. So we have 4 iron. We have 2 times 2, which is 4 iron. We have 3 times 2, which is 6 oxygen. We have 2 times 3, which is 6 oxygen. So everything is balanced out there. This next problem looks a little more complicated. It's got a lot more numbers in here, or sorry, a lot more letters in here. And that's going to make you freak out at first, because you're going to look at that and go, where do I even start? Well, again, I usually just start on the left and work my way right. So the first element I come across here is sodium. Let's see how many sodiums there are on the left. I see 1 sodium atom in this species. I see no sodiums in this. So there's 1 sodium on our reactant side. Let's cross the arrow into our product side. I see 1 atom of sodium here in sodium nitrate. Plus we have lead chloride. There's no sodium in there. So now we have 1 atom of sodium on the left, 1 on the right. We're good there so far. Now let's go to chlorine. So we have chlorine right here in sodium chloride. We have none in lead nitrate. So we have 1 chlorine atom on the left. Come over here, none in sodium nitrate. And then we have 2 chlorines in lead chloride. So we're going to need to multiply this sodium chloride over here by 2. Okay, now we just changed the number of sodiums we have, so let's reassess sodium. All right, now we have 2 sodium atoms on the left. We have 1 on the right, so we need to multiply this sodium nitrate by 2. Now, let's go on here to our lead nitrate. So let's look at lead. We've got 1 atom of lead on the left. Let's see how many we have on the right. We have 1 atom on the right, so we're good with lead. Let's look at our nitrate right here. We have NO3. We have 2 of those. Now, some of you might be thinking, why are we keeping NO3 together? Why aren't we counting individual nitrogens and oxygens? And in this case, I've just recognized that this is a salt reaction. So this is lead nitrate. And so if you can think of these in terms of salt, when you recognize it as a salt reaction, it simplifies it a little bit. So we can treat nitrate as a whole unit here. So we have 2 nitrates over here. We have 1 nitrate and sodium nitrate, but we put a 2 in front of the sodium nitrate. So we have 2 nitrates on the right. We have these 2 nitrates on the left. And so we're actually good. So we'd need a 1 in front of the lead nitrate, 1 in front of the lead chloride. But like in a math equation, usually if we have a 1 times something, we will drop those. And so this equation will just balance out this way. It's 2 sodium chlorides plus lead nitrate goes to 2 sodium nitrates plus lead chloride. That leads us to our last reaction down here, where you have KO2 plus CO2 going to K2CO3 plus O2 gas. So let's just start with potassium here. Noticing there's 1 potassium here on the left. There's 2 on the right. So let's go ahead and multiply that by 2. Now I could go on to oxygen now, but I'm noticing oxygen is kind of everywhere. Let's come back to oxygen later. Let's talk about carbon now. So we have 1 carbon on the left. How many do we have on the right? We have 1 on the right. All right. So potassium and carbon are good. Let's now count oxygens. So over here we have 2 times 2, which is 4 oxygens, plus 2 more oxygens, which brings us to 6. Then on the right, we have 3 plus 2, which is 5. Okay. So now we have 6 on the left, 5 on the right. It would work out really easily if we could say that there were 1.5 O2s over here. So 1.5 times 2 would be 3. So 3 plus 3 would give us 6. Now, in this case, we'd have 6 oxygens on the right, 6 on the left, but you're not allowed to have fractions in equations. You need to have whole numbers. So what we're actually going to end up doing here is multiplying this whole equation by 2. So that's going to give us this, where we're going to have 4 KO2s plus 2 CO2s plus 2 K2CO3s plus 3 O2s. Let's double check that everything is right in here. So we have 4 potassiums We have 2 times 2, which is 4 potassiums. Now we have 2 carbons on the left. We have 2 times 1, which is 2 carbons on the right. We have 4 times 2, which is 8, plus 2 times 2, which is 4. So we have 12 oxygens on the left. Over here we have 2 times 3, which is 6, and we have 3 times 2, which is 6. 6 plus 6 is 12. So we have 12 oxygens on the left, 12 on the right. Now, you might be thinking as you're looking at that, that some of my steps seem kind of random. How I approached it seemed kind of chosen at random. So what I would say to that is that in part you're right. A big part of balancing these equations comes from experience and just practice. A lot of these, you're going to get a little bit of an intuition for how to approach these just by doing them over and over again. And that's the best way to get familiar with balancing chemical equations. You're going to, generally, I like to start on the left, look at the first atom, try and balance that. Then I go to the next one. If I see that it's everywhere like this oxygen was, and especially if I see that oxygen is by itself in one spot, I'll put that one on the back burner. Usually if there's one pure element by itself like this, that's going to be the easiest to balance, and so you're going to want to do that last. Okay? But that rule isn't always going to hold up. Sometimes it's just going to be complicated, and it's just going to come through trial and error. Okay, so let's move on then to iCLICKER quiz. And I'm going to ask in this one, what is the coefficient of boric acid, H3BO3, when the following chemical reaction is balanced? Now this one is a lot more complicated than the ones we were just doing. There's a lot more going on, but we're going to do the same thing. Let's just start from the left. Now we're going to first run into sodium. So here we have 2 atoms of sodium in this Na2B407 dot 10 H2Os. Now I'm going to point out right here that this dot means that this guy is hydrated. So this has a decahydrate around it, so it has 10 waters around it. But let's go back to our sodium. So we have 2 atoms of sodium here. Do we have any other sodium on the left? No. Let's come over here to the right. We have 2 atoms of sodium in sodium chloride. So let's give that, or sorry, we have 1 atom of sodium in sodium chloride. We need to change that to a 2, so let's multiply it by 2. Now we have 2 sodium chlorides. Now let's go on to the next atom, which is boron. We have B4 over here. We have 4 borons. Are there any other Bs over here? There's not. Are there any borons right here? There's some in boric acid, H3BO3, but there's only 1. So we know we're going to need to multiply that guy by at least 4. All right. Let's come back to our oxygens and hydrogens because I did this a little out of order. The reason I have this 2 here in front of HCl is because the only place chlorine is in this equation is in HCl and in sodium chloride. And I already put a 2 in front of sodium chloride, so we know there's 2 atoms of chlorine, so there's going to be 2 over here. All right. Now let's count up our oxygens because that comes after boron. On the left, we have 7 oxygens plus 10 times 1, which is 10. So we have 17 oxygens on the left. Over here on the right, we have 4 times 3, which is 12 oxygens plus 1 more oxygen in water. So that's 13 on the right. We need 4 more. Easiest place to get those are going to be in our water. So let's multiply that guy by 5. The reason we multiplied it by 5 is we needed 4 more, and we already had 1. So 4 plus 1 is 5. Now let's count up our oxygens just to double check here. We have 7 plus 10, which is 17. Then over here we have 4 times 3, which is 12, plus 5 more from our water. That's 17. So we have 17 oxygens on both sides. Now let's count up our hydrogens. Hopefully these balance out so we don't have to do anything else. We have 10 times 2, which is 20 hydrogens from water, Then we have 2 times 1, which is 2 hydrogens from HCl. So we have a total of 22 hydrogens on the left. On the right, we have 4 times 3, which is 12 hydrogens. And then we have 5 times 2, which is 10. 10 plus 12 adds up to 22. So we have the same number on either side. Now let's read the question one more time, which is something you should do on exams, and to figure out what exactly are we trying to answer. The question is, what is the coefficient of boric acid, H3BO3, when the following chemical reaction is balanced? Okay, we've balanced this guy now. So our coefficient in front of boric acid is a 4. And that's the answer to that question. All right, so let's talk about these chemicals just for fun. This Na2B407 decahydrate is actually borax. It's what you use for cleaning. I don't know how many of you actually use it for cleaning. It's not as popular anymore. I actually use it in my lab for reactions fairly often, but I don't actually use it for cleaning. And then this boric acid over here is a flame retardant that people use. So exciting. All right, let's go on. There is a type of reaction that is extremely common and very important, and so we give it its own name, and that is the combustion reaction. So combustion is what makes civilization possible as we know it, and it's what gives us fire. So a combustion reaction specifically, though, is a reaction between fuel and oxygen that is very rapid, and then it generally forms CO2 and water as products. But the formation of CO2 and water as products is not a strict criteria, but a rapid reaction between fuel and oxygen is your combustion reaction. So an example of this is hydrogen gas, just like the hydrogen balloons I've exploded in class a few times. So in this case, we have 2 moles of hydrogen gas reacting with every 1 mole of oxygen, and that forms 2 moles of water gas. So it seems kind of counterintuitive a lot of times when you first see this to think that a flame is producing water, but most flames actually do produce water and a certain amount of CO2. Now you'll notice in this hydrogen gas reaction, this is a combustion reaction, but we didn't form any CO2, we just formed water. But we had that critical element of hydrogen reacting very rapidly with oxygen to form water vapor, or water gas, sorry, it's not a vapor. Now, a reaction that does produce CO2 is the reaction of ethane. So this is a 2-carbon chain. Those carbons are saturated with hydrogen, so this is C2H6. And with ethane, it takes 2 moles of ethane to react with 7 moles of oxygen. And this then goes to 4 moles of CO2 gas plus 6 moles of water. Another example is butane. Right, this is used a lot in homes for heating. We burn butane. Butane is a 4-carbon chain saturated with hydrogens. And so it takes 2 moles of butane to react with 13 moles of O2, and we get out 8 moles of CO2 plus 10 moles of H2O. And it'd be perfectly reasonable for me to ask you to balance one of these combustion reactions. Now what I'm showing you here are examples of complete combustion where all of our carbon is being used up and turned into CO2. This doesn't happen in every combustion reaction. Most combustion reactions are what we call incomplete combustion reactions. So some of your carbon is converted into carbon monoxide or into soot or other byproducts that contain carbon. So when you think about wood, let's say you take a tree, chop it down, you make a campfire out of it. Hopefully the tree was dead, otherwise it won't burn very well. But once you're burning that wood, you're left over with a lot of burned up logs, right? With charred logs, you also get a lot of smoke out of there. CO2 is not a visible gas, and so that smoke is other byproducts, other carbon products saturated with oxygen and hydrogen. And so most combustion reactions are incomplete. So you get incomplete reactions when you have a limited amount of oxygen. So if you don't have enough oxygen to use up all of all of the carbon, or when other reactions are more favorable than complete combustion, or when other reactions are happening more quickly than complete combustion. So when you're burning wood, it's more favorable to form other products than CO2, just because of the speed at which those products are formed. Right, so I could give you a question like this. What is the coefficient of O2 right here when the combustion reaction below is balanced? So right here we have C3H8. C3H8 is propane, which is marketed by Hank Hill.
I provide the people of this community with propane and propane accessories.
Right, but like Sarah Palin, he doesn't really have much to do with chemistry. But we want to balance this reaction of propane with oxygen, and we get out CO2 and water. Okay, so let's start with carbon. We have 3 carbons on the left. We have 1 carbon on the right, so we're going to need to multiply that CO2 by 3. Now let's go to hydrogens. We start with 8 hydrogens on the left, and over here we have 2 hydrogens on the right. How do you make 2 into 8? You multiply it by 4. Now let's count our oxygens, see how many of those we have. All right, so on the left we have 2 oxygens. On the right we have 3 times 2, which is 6, plus 4. So we have 10 oxygens on the right. We just started with 2. How do we turn 2 into 10? We got to multiply it by 5, right? So the answer there is 5. So when you grill your steak on your grill, for every 5 moles of oxygen, you use up only 1 mole of propane to cook, which is just a fun little fact. All right, so everything we've been talking about so far falls under this umbrella that we call stoichiometry. So stoichiometry is just a quantitative relationship between the number of moles of products and the number of moles of reactants that you get in an equation, okay? So we're going to be practicing stoichiometry and problems with stoichiometry for a little bit. But the big part of stoichiometry that is important are the stoichiometric coefficients. So these balancing of equations. It's super important. It makes up a huge part of what chemists actually do, okay? Now let's look at this equation right here where we have 2 moles of aluminum reacting with 1 mole of rust to produce 2 moles of iron and 1 mole of aluminum oxide. Okay? So in this, we have our stoichiometric coefficients, right? In front of the aluminum, we have a 2. In front of the rust, we have a 1. In front of this iron, we have a 2. In front of the aluminum 2O3, we have a 1. So these stoichiometric coefficients give us a mole ratio, or the ratio of each species that we need in our reaction, right? So if we're trying to figure something out, like let's say we're trying to figure out how much rust we're going to use up if we react with aluminum, what we'd take is the number of moles of aluminum and multiply it by the mole ratio between these 2 species. So for rust, you'd get 1 mole of rust, which would just be the 1 right here, for every 2 moles of aluminum used up. So you just take the number of moles of aluminum, times it by 1 mole of iron, or sorry, 1 mole of rust divided by 2 moles of aluminum, and that will give you the number of moles of rust out that you're going to use up, okay? So we're going to practice with that a bit. This first one, this first iCLICKER quiz asks how many moles of iron can be formed by this reaction down here, the one we've just been talking about, when 0.432 moles of rust are present and you have excess aluminum in this reaction. So this is the thermite reaction I showed you in class, where it got really big and bright. Somebody told me not to look in the pot. I told them, you don't look in the pot. Anyways. So let's look at the question. Question is saying we have 0.432 moles of this species right here with excess aluminum. That means we have as much aluminum as we need, and we're going to completely use up the rust, right? So the way we would do this is we'd take our number of moles of rust, which is 0.432 moles, then we times it by the mole fraction here. The mole fraction between rust and aluminum is we need 2 moles of aluminum for every 1 mole of rust, so that's 2 divided by 1. So we're just literally going to take 0.432 and multiply it by 2 here. Then our moles of rust are going to cancel out on top and bottom, and we will be left in units of moles of iron, and we get out a value of 0.864 moles of iron. Let me know if you have any questions about that. All right, now I could give you a problem where I want to know how much product we get from the amount of reactants used. So in this question right here, I'm asking when 34 grams of iron are oxidized, I left out the word are, how many grams of rust are formed? All right, so in this case, we have a reaction, but we'll notice there's 1 atom of iron on the left, 2 on the right, so this guy is not balanced out. But this is a reaction we've already balanced, so I will just give you the answer on this one. But don't be surprised if I give you a problem like this with a reaction that's not balanced. So you have to balance the reaction, then do your conversions from one species to another. So here we're starting with 34 grams of iron, and we need to figure out how many grams of rust are formed. The first thing we need to do is convert our iron into moles of iron. So what we're going to do is we're going to take 34 grams of iron, divide by the molecular weight of iron, which is 55.8. All right, then our grams will cancel out. We're now in units of moles of iron. We don't care about moles of iron, we care about grams of rust. So we're going to first need to figure out how many moles of rust we got. So we're going to take this moles of iron that we have and multiply it by our mole fraction. We need 2 moles of rust for every 4 moles of iron. And so our mole fraction is going to reflect that. And then our moles of iron will cancel out top and bottom. Now we're left in moles of rust. Again, we don't care about moles of rust, we care about grams of rust. So we're going to need to multiply our moles of rust by the molecular weight of rust, which in this case is given in the question. It wouldn't be unreasonable for me, though, to ask you to calculate that from values on your periodic table. But now our moles of rust will cancel out, and we will carry all this math through, and when we do, we will be left with 49 grams of rust, right? Now that looks like a lot of steps, and it is, let's see, it's 1, 2, 3 steps to get our answer. Then sometimes it'll be a little more than that, but just think through conversion factors. What do I need to convert from moles, or from one value to another? If I give you grams of one species, you can rest assured you're always going to turn that into moles of that species, and you're going to find the moles of the species you're trying to produce. And then if I ask for grams of that, you're going to convert it to grams. If I ask for liters, you'll convert it to liters, etc. Now let's look at a problem if I want to know how much reactant is needed to give a certain amount of product. All right, let's look at the Haber-Bosch process. So this is a catalyzed reaction. I haven't taught you about catalysts yet. We'll get into those later. But using this reaction, the world produces about 3,300 metric tons of ammonia every day. So we want to know, in this question, how many grams of hydrogen gas does that require? So if we look at this equation, let's double check that it's balanced. We have we have 2 atoms of nitrogen on the left. We have 2 atoms of nitrogen on the right. We have 3 times 2, which is 6 atoms of hydrogen on the left. We have 2 times 3, which is 6 atoms of hydrogen on the right. All right, this guy's balanced. So now we know how many metric tons we're producing in products, and then we just need to convert that into reactants. All right, so all we're going to do here is take our value, our mass of ammonia that we got. By the way, 3,300 metric tons is equal to 3.3 times 10 to the 9th grams. We're going to divide that by the molecular weight of ammonia, and we're just going to multiply that by the mole fraction between hydrogen and ammonium. You'll notice in the mole fraction, the species you're trying to figure out is always on the top. The species you're starting with is on the bottom. When we look at our mole ratios in our equation, we have 3 moles of hydrogen, we have 2 moles of ammonia. So our ratio is going to be 3 to 2. We're going to multiply that then by the molecular weight of hydrogen, because the question asks how many grams of hydrogen does that require. Then when we carry all this through, we're going to be left with 5.8 times 10 to the 8th grams of hydrogen. So this Haber-Bosch process was developed by Fritz Haber back in 1918. He's an interesting looking fellow. I think he looks kind of sad, but other people have disagreed with me in the past. But this process is still super important. So about a third of the Earth's human population is kept alive by fertilizer produced in part using this process. And about a half of the proteins in your body, or about half the nitrogen in the proteins in your body come from this process. Anyways. But so if I ask you, if I give you how much product, you should be able to figure out how much reactant was used to get that product, right? And if I tell you how much of one reactant is used up, you should be able to tell me how much of a different reactant is used up. Basically, if I give you an equation like this and I tell you how much of any one of these species was used up or produced, you should be able to tell me exactly how much of every other species in the reaction is used up. So in this one, specifically, I've got a formula here that is used in gold extraction. So basically they take this ore, they crush it up, they melt it, and then they throw in sodium cyanide in here. And then the question would be how many grams of cyanide are needed to extract 100 grams of gold? So in this case, we would take our grams of gold, which is right here. We would turn it into moles. We always start with the grams, turn it into moles. And then we're going to multiply by our mole fraction here. And we have our sodium cyanide here. It has 8 moles of that. We have 4 moles of gold. So we're trying to figure out cyanide. We have the moles of gold. So we're going to put 8 moles of cyanide on top, 4 moles of gold on bottom. Now this question is a little tricky because it is actually asking how many grams of cyanide, and we're starting with sodium cyanide, and so we actually need to convert our sodium cyanide into cyanide, which is a little tricky. When you throw sodium cyanide in water, it's going to dissociate, so for every mole of sodium cyanide you throw in, you're going to get 1 mole of cyanide. So the ratio between cyanide and sodium cyanide is just 1 to 1. And then, of course, we multiply by the molecular weight of cyanide, which is 26.018, and we get out the number of grams of cyanide used in this process. Okay, now, just for fun, let me show you. This is a big chunk of gold ore, and if we're going to refine that, we'd get about 30 grams of gold out of an 860 kilogram block of gold ore, right? So it's not a ton. It's kind of shocking how little we get out. Oops, but it's kind of fun. All right. So a typical question I could give you could look like this. All right, this is a balanced reaction for the complete combustion of gun cotton. Assuming our gun cotton ball weighed 0.66 grams, how much CO2 did we produce by combusting it, right? So in this case, our gun cotton is right here. It's this C6H7N3011 species. Got its molecular weight there, but again, you could just have to calculate that yourself. We're trying to figure out how much CO2 we're producing. So again, just like we've done before, we take the grams of gun cotton we're given in the question, 0.66 grams, divide by the molecular weight of the gun cotton to get it into moles. We're going to multiply by this mole fraction. We have 24 moles of CO2 divided by 4 moles of gun cotton. That's, again, just this 24 moles of CO2 divided by this 4 moles from our equation. And then we're going to have to multiply by the molecular weight of CO2, which is 44 grams. When we do all of that math, it comes out to 0.59 grams of CO2 is combusted when we burn 0.66 grams of gun cotton. Right? So you should be able to follow that. And if you have questions about that, we will still have TAs signing up for specific times in TA labs, and I'll give you some details on how that's going to work in a follow-up video. But feel free to reach out. The average person exhales about 900 grams of CO2 each day. So you're producing about 1 kilogram of CO2 every day. And so this amount that's produced when we burn that small piece of gun cotton is about how much you produce every 15 breaths or so, depending on your size, how big you are weight-wise. All right, now a quick note about stoichiometry with gas. So all of this stoichiometry stuff still depends on mole ratios, but with gases, it's often a lot easier to measure its pressure, volume, and temperature than its mass, right? Especially for gases that float, can be really complicated to measure their mass. So we usually just measure their pressure, volume, and temperature. And then at least for this class, we can pretend that these gases behave ideally. We can use our pervert equation, PV equals nRT, solve for the number of moles that way. So, right, so then number of moles is equal to PV over RT. So if you have the pressure, volume, and temperature, R is a constant, you can figure out how many moles of gas are present, right? So if I asked you a question like this, so in automobile airbags inflate by the rapid generation of nitrogen from sodium azide, which is just sodium Na3. And this guy spontaneously generates nitrogen when you give it room to do that. And so it produces sodium solid plus nitrogen gas. And this sodium solid doesn't react because it reacts with oxygen, not nitrogen. So you're generating gas in this way. The question is, how many grams of sodium azide are needed to produce sufficient N2 gas to fill a 48 by 48 by 25 centimeter bag to a pressure of 1.2 atmospheres at 15 degrees Celsius? Okay, so we're going to have to do some things here. We're going to have to calculate our volume from those dimensions I've given you. So our volume, right, will be equal to 48 by 48 by 48, 20, or sorry, by 48 times 48 times 25 centimeters, and that'll give us cubic centimeters. It'll give us 57,600 cubic centimeters. And from your conversion chart, which is on your equation sheet, you should know that a cubic centimeter is equal to 1 milliliter. So now we have our volume. And we have our pressure of 1.2 atmospheres, and we have our temperature at 15 degrees Celsius. We're going to have to convert that into Kelvin. But from these values, we can calculate roughly our number of moles. So our moles is equal to our pressure times volume divided by RT. So we have 1.2 atmospheres times 57,600 mils divided by 100 mils, get us into liters. We have to get it into liters because our R value is reported in liters, and we need those units to cancel out. So we plug in our R value. And you'll notice right here we've converted from 15 degrees Celsius to Kelvin by adding 273.15. When that all comes together, we get 2.92 moles of nitrogen gas. Okay. Now that wasn't the question though. We weren't worried about how many moles of nitrogen gas. The question was how many grams of sodium azide are needed to make 2.92 moles of nitrogen gas. So now that we have the moles of nitrogen gas, we need to convert to moles of sodium azide. And we're going to do that using our mole ratio. So we're going to do 2.92 moles of sodium gas times 2 moles of sodium azide. Again, that's just the 2 from the equation, divided by 3 moles of sodium gas. So that gives us a total of 1.95 moles of sodium azide. Now we need to turn that into grams. we're going to just do that by multiplying 1.95 moles of sodium azide times its molecular weight of 65, and we get a value of 127 grams of sodium azide. Okay, so you should be able to take values like that, like dimensions of a bag or dimensions of a space, the pressure and temperature, and figure out the number of moles needed in a reaction. Let me give you another question here. At standard temperature and pressure, how many liters of O2 are needed to burn 32 grams of methanol? How many liters of CO2 are produced? All right, here you got to remember standard temperature and pressure means that at a temperature of 0 degrees Celsius and a pressure of 1 atmosphere, right? So the question is, how many liters of O2 are needed to burn 32 grams of methanol? So methanol is this CH3OH guy right here. So first thing we got to do, figure out how many moles of methanol we burned. So we're going to convert methanol into moles by dividing the grams we used by the molecular weight, which in this case happens to be 32 grams. So that's 1 mole of methanol. We're going to have to multiply by our mole fraction, 3 moles of O2, right? So divided by 2 moles of methanol. Then we find that we burned 1.5 moles of O2. Now we need to turn that into a liter. So the question is, how many liters of O2 are needed to burn that much methanol? So we got to turn that into a volume. So how many moles, or how much volume is taken up by 1.5 moles? Well, then we need to use PV equals nRT to calculate the volume based on the pressure of 1 atmosphere at the temperature of 0 degrees Celsius or 273.15 Kelvin. Now at standard temperature and pressure, there is actually a cheat, right? So the molar volume of any gas at standard temperature and pressure is 22.4 liters. So we actually don't have to calculate the volume for 1.5 moles using PV equals nRT. We can just say 1 mole is equal to 22.4 liters. If the pressure is not 1 atmosphere or the temperature is not 0 degrees Celsius, you do have to use PV equals nRT. But if you're at standard temperature and pressure, you get a cheat. So we're just going to multiply 1.5 times this 22.4 liter molar volume. We're going to find that we needed 33.6 liters of oxygen to burn that much methanol. Now the next question, how many liters of CO2 are produced? In this case, we're doing a very similar thing, except we're starting with 32 grams of methanol, turning it into moles and multiplying it by the mole fraction for CO2, not for O2. So the mole fraction here is 2/2. Again, we're at standard temperature and pressure, and so we can cheat and say that this CO2 produces or takes up 22.4 liters of volume for 1 mole of gas. And so when we carry all that math out, we find that we produce 22.4 liters of CO2. Again, you can only use this cheat where the molar volume is 22.4 liters at standard temperature and pressure. If you're at any other temperature and pressure, you actually have to calculate the volume used up. All right. So let's ask this question. What volume of O2 is needed for the complete reaction of 250 milliliters of nitrous oxide at standard temperature and pressure? So in this case, we're trying to figure out the volume of O2 needed. We're saying we used up 250 milliliters of NO gas. We want to figure out how much O2 gas is produced, or is used up, sorry. We're at standard temperature and pressure, so we know their molar volumes are 22.4 liters. So we can just take this value of 0.25 liters, which is the volume of NO used up. We're going to divide that volume by the molecular, or the molar volume, which is 292.4 liters. We're going to multiply that by our mole fraction here, which would be 1 mole of O2 for every 2 moles of NO. I'm going to again multiply that by our mole fraction, or sorry, our molar volume of oxygen, to figure out that we used up 0.125 liters of O2. Right. So in this case, since we're at standard temperature and pressure, you'll notice you could have skipped this first step and this second step, just multiplied by the mole fractions. But if you don't follow that logic, I would follow through every step of this process, not give up any steps. You're always going to want to convert to the number of moles of your starting species. So in this case, we started with a volume, went to the number of moles of NO, then we multiplied by our mole fraction, and then multiplied by a second ratio that got us to the value we wanted. We could be asking how many grams of oxygen, how many liters of oxygen. I could give you the volume of the oxygen and the I could give you the volume of the oxygen and ask you to calculate the pressure of the oxygen at the beginning of the reaction. All sorts of fun ways I could twist that. Okay. All right. Now that is the end of the lecture. Again, if you have any questions, feel free to reach out to us. I will be sharing some more details about how TA Labs will be working. And as we go forward, if you have any concerns, please let us know right away. All right.